Hello, welcome to today's lecture about decision trees and random forests. And this is our agenda for today. First of all, we'll talk about decision trees and understand how they work. And then we will see the problems of the decision trees and how can we easily address them and make them to really, really good classifier or regressor, so like a really good estimator. So first of all, really important question. Let's think about, is your date evil? So imagine we have to answer this important question. And what is our experience with good and evil? So we have these superheroes, we have these supervillains, and based on our experience, based on our data, we need to decide if our date is evil or good, or maybe on other people. So this is the database for this. So first we ask, so our experience is we will ask for this 6 attributes: if the person wears a mask, if it wears a cape, if it wears a tie, if it has pointy ears, if the person smokes, and then we will measure the height and see which height the person has. And based on these 6 attributes, we will decide on if the person is good or evil. And so so as you see here, we have 6 examples, and we have 3 for us to decide on based on this example. Okay, so yeah, blue plus means it wears a mask, minus means it doesn't wear a mask, and so on. So this is our experience with good and evil. And this is the data set we will be discussing this thing about. But before, let's review that solution to machine learning tasks are called hypotheses. So because usually we were talking about classifier or regressor, but obviously we have some other tasks. So in all, we can talk either about predictor or estimator or hypothesis. So this basically means the same. It's the solution to some machine learning test, to the model which we have in the end. And these hypotheses have to be represented in some representation scheme. So yesterday, we had this hyperplane representation. We said we allow for our hypothesis to be hyperplanes. And today, we will choose the tree representation. So our hypothesis will now be a tree. Now let's go to decision trees. So this here is how a decision tree looks like. So if you never saw such a representation, we always in a tree have a node, a root node. So those nodes which have children, they are called interior or inner nodes. And those nodes which don't have any children, they are called leaves. And this first node, it's called a root node. So our root of a tree. And each of those interior nodes in a decision tree corresponds to a question. So we can basically ask any question, for example, related to features. So we are asking questions on our features. So first we need to choose on which feature we are asking the question, and then we need to decide on the threshold. So for example, in this case, if the feature would be a numerical feature, the numerical question would be if our feature is less or equal than a, some threshold a, and if we will answer it with yes, then we'll go to the left, or with no, we go to the right, and we keep on asking. Or it could be a categorical question. If our feature, for example, if our feature x is blue, red, or white, so it doesn't have to be always numerical question. We also can say which class it belongs to. So for example, we have a feature of which has these 3 category values, and we can ask the question either to which of this class our feature belongs to. Then we can say, okay, blue go to the left, white go to the middle, or red go to the right. Or we can pose this question: if our x is blue, go to the left, or it's something else, go to the right. So we can basically first decide on what we ask and then which answers we get. So either we get binary answers, yes or no, or we're allowed to ask, so have many partitions. So for today, and also this is how it's done, we will focus on these binary questions, and we will shortly discuss that there are other possibilities. It's basically our choice, and our choice is just based solely on the computational issues, because everything which is binary is easier to work with. So in our case, we will say yes or no. So the question on feature here, so basically the question consists of a pair, feature and a threshold, or feature and a category which it belongs to. And then we say yes or no. And when we are not saying anything, those are leaf nodes, they will tell us the label. So here, these leaves correspond to target label, some label which will put it. So we will ask this, then we go here, for example, then we are here. And if our example answered these questions like this, it will go, receive this label. So this is basically how it works. And here on the right, you can see what actually those questions do to our feature space. So our features, we have here only two features, x1 and x2, and this is what our questions do to our feature space. So imagine you had here so this is already a finished partition, but how it starts. So first we have our feature space, we have a feature x1 and the feature x2. And we're asking just one question. So we are always allowed to ask one question at a time. And so we're asking, for example, is our feature x less or equal to some threshold a1? And this question corresponds to this partition. So we partitioned our feature space into regions first. Then we will ask second questions. If our feature x1 is greater or equal to this other threshold, and then we'll partition it here. And when we see with all the yeses, we already have the region here, which already is classified as some label. And then we have second partition, so we stopped asking on this feature. We are now asking on this x2 feature, and this will be the fourth question. The next question on the, this will be the next question, A3, whether x2 is less or equal to A3, and here is 4. So this is how we can partition our space, and then those R's are basically the classes which belong to those partitions. So if the point afterwards will go something here, then it will classify accordingly. So this is basically how you go. So what we will represent it is always a tree. So the trees is a representation, and this on the right is just for you to understand it, how the partitioning goes. Okay, so yes, and if we have several examples which fall here, so we need to decide on the label, then we will assign the label which is mostly here, which happens most. So if, for example, we have several examples that come here in this region, and so we will take the majority. Also, for now the presentation, let's talk about classification. So we will talk about labels. Afterwards, we will see that they can easily be used for regressions, but now just think of these leaves as some class labels. And if we have some examples which have different labels, we will take the label for this which is most present. And this is enough for theory. Let's go to the example. Here is an A decision tree for this data set. And the question is this tree consistent? That means, would it classify every example that we have correctly? Take a minute and check. Yeah?
Alfred would be classified as equal?
Yes, correct. So we have, if we do it like this, then we won't get our examples correctly. Correct. So the effort is good, but he doesn't smoke, he doesn't wear a mask, and already is classified as evil. So in this case, this tree is not consistent. What can we do if we have a tree which is not consistent? So remember, if our tree is not consistent and we want it to be consistent, so at some point we don't want, but if we want, we need to split, to continue splitting. So that means we can, for example, split like this. We can say, if a person doesn't smoke, doesn't wear a mask, we will ask for a tie. And then we can separate the Alfred, because Alfred wears a tie, and everybody else who falls in this answers doesn't. So with a tie, we will already separate our Alfred and all other persons, and this tree is consistent. So every time when we notice our tree is not consistent, that means it classifies something wrong from our training data, we can keep on splitting. Okay? And the question, of course, is it always a good idea to split or not? And the answer is, we need to think of our bias and variance stuff. So remember, or recall, what is the bias and variance of an estimator? So high bias means there is something wrong with our algorithm that we cannot even classify our data our training data correctly. So basically, high bias means underfitting. So we cannot even classify our training data correctly. High variance means we can classify our data correctly, but only our data, our training data. If we keep on getting more test examples, then we will get wrong. So we will vary too much. So that means we're overfit. So high bias means underfitting, high variance means overfitting. So if you think of a function which depends on the function of depth. So depth means the lower we go on our decision tree, the higher the depth is. Then you can get an idea if our decision tree is small, do we have high bias or high variance? Or if our decision tree is large, do we have high bias or high variance? Do you have an idea? Yes?
If it's smaller, we have high bias, and if it's larger, we have high variance.
Yes, correct. If it's small, then at some point, as we saw just right now, we couldn't classify our training data correctly. That means high bias. And if it gets larger, we're simply memorizing our training data. And if we get new training data, then our variance would be high, because we will vary a lot on this. So correct, yes. So if we think of it as this, then we can answer our question, maybe. So low depth, high bias, high depth, high variance. Then what we ideally want to have is the smallest tree that fits the data. So we ideally don't want to go around splitting here and there and everywhere. We would actually prefer to have the smallest possible tree that fits the data. So that would be our ideal decision tree. And the problem is, of course, that finding the small decision tree is impy hard. And impy hard is really hard. So we probably can forget it, at least at this point. But it's no problem, because we will still get to approximation at some point. But for the first, so what we ideally really would like to have the smallest tree. So this whole notion of smallest tree corresponds to our idea of Occam's razor, which we talked about yesterday. So we preferably always want to have such estimator which has fewer assumptions or fewer, so the smallest possible. But in this case, we won't get it so easily. But for this database, we can. So maybe it can take a couple of seconds and try to make the smallest tree. So in this case, I would ask you to make the smallest tree in amount of splits, not in amount of depth, but try to make as small as few splits as possible in order to classify the data set correctly, trained data. So how many splits do we have? Two. Okay, yeah, that's nice. And which ones?
For example, cape and tie.
Cape and tie. So what do you want to ask? If the person wears a cape, so first cape, and if yes, or in my, I had here yes. Oh, okay, maybe that was not a good idea too. I think this doesn't work. Okay, so cape, yes, or no, and then afterwards, if it's yes, it's what?
If he wears or she wears a tie.
Yeah, no. So when I go to yes, then tie, tie, and then yes or no. What would I classify it like?
Yeah, if tie no, then good.
Okay, if tie no, then good. Okay.
Yes, then we have evil.
Okay. Evil. Okay, and here, if it doesn't wear a cape, what happens here?
It doesn't need actually. Exactly.
So everybody wears a cape?
Then evil.
Evil. So it,
Yeah. Can we pass just like this?
if you answer the cape, so if you ask first for a cape, then Alfred will go to be evil. Because you're going always your question from the root, and then you answer it, and then you keep on asking. Okay, so if no one has an idea, so this would be my solution to this. So I'm first also asking for a cape, and if it's yes, it's already good, because we only have the most two who we don't have to ask for any more questions. And if the person doesn't wear a cape, then we'll ask for the height. If it's greater than 108, then it's good. Otherwise, it's evil. So this will be the smallest tree here in amount of splits, just for you to see how it could look like. And the thing is, since we said that we cannot probably get this smallest decision tree because it's NP-hard, we still have to do something. And what we will do is we will do the greedy idea. And what greedy basically does, it optimizes each step by step. So it doesn't look far ahead. It just say, okay, presented with all the data I have right now, what's the best possible decision at this moment? So if you imagine this, if I would be packing a bag, and I want, so my idea would be to pack as much weight as possible, for example, or the biggest amount, or the more expensive amount. So first, greedy will say, okay, first give me the biggest object and pack it in the bag, and then take the biggest one of the remaining one and pack it in the bag too, and so on. So this is what greedy does. At every step, it tries to choose the best possible decision, not looking far ahead. So sometimes if you pack in the bag, it's not always a good idea to put something big in it, because then it would influence your decision afterwards, and then you cannot maybe pack anything else there. And if you put second best, then you could maybe keep on putting and so on. So this is why greedy idea does not always work. I mean, it works always, but does not give always optimal decision, optimal result. At some points, it does, actually. So if you calculate in shortest path algorithm, for example, there is this Dijkstra algorithm, which uses this greedy idea and still optimal. And so this is one way or another included in your Google Maps things with some variations. But in this case, we have to do it because there is no possible way. So we will say for decision learning, greedy means at first we will decide which loss function will describe the effect of the split, because we will split in split by split, and we need to measure what we are doing when we're splitting. And then once we decided on that, we will say, okay, we will start with a new root node, so in the beginning, and then we will try all the features that we have and all possible splits. So that means we will try all features and all possible thresholds. All that we can have, and then we will calculate our loss function, and then pick one that minimizes the current loss the most, like minimizes it completely, and then we will repeat it from step 3. So starting, split, trying all features, all thresholds, then we will split, then it will continue going through all features, all thresholds, and all nodes, and see where we can achieve the best decrease in loss function, and then repeat and repeat and repeat and so on. So this would be the idea for decision learning. And for now, we don't talk about how we stop. So here you see there is no stopping criteria here. This we'll discuss a little bit later after we actually do the steps 1 to 4. And afterwards, we'll decide how we will stop. So what is the effect of a split? So if we split what we in the end want to have in our leaves, we want to have pure leaves. So we want our data to our leaves to be pure, so that only one label is present in all examples there. So that should be ideally the case. This is not always the case. That would be really ideally, because then if our example falls into this tree, we will most certainly say it has this label. So if the label, if the leaf has some examples which have different labels, then we are not so sure. So what we ideally want to have is we want our leaves to be pure, to have only one label. And that means our loss function, we need to measure impurity of set of the points, whether it's leaf or it's a node. So we have here all the time, we have some set of the points which fall here. So in the end, we have all the points, then we have split, then we have only the points which answer the first question as yes, and so on. So at each node and each leaf, we have some amount of points, and we need to measure the impurity of the set which is in there. And there are 2 good ways to do it: Gini impurity and entropy. So there are also several, but they are not interesting. And first, let's talk about the Gini impurity, because this is basically our hyperparameter for decision trees to choose on our loss function. And what Gini impurity basically measures is, it says, okay, if I have the set S, here, for example, this is my node, and I set S. So it says how many. So the S measures the number of all examples, and the SK measures. Contains. So the set S contains all examples, and set K are the examples in S having their label, the class label K. So if we have, for example, here such a data, if we have some pluses, plus, plus, and plus, and here maybe minus, 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 and again plus, or maybe even more pluses, then our S plus would be all those 5 pluses. So the set would be containing these 5 pluses, obviously the coordinates of them, and the cardinality. So those straight lines mean the cardinality, the number of points in the set. So the cardinality of set plus would be 5 in this case. So we just count the number, and they have 5. Cardinality of set S would be 8. And that means that the probability of us picking a label with class K out of the set is equals to 5 divided by 0. So this is what we're interested in. Is we want obviously this probability in the end to be like high for one class and 0 for all other classes. And the Gini impurity is defined for all the possible classes which contained in here, the probability of picking the class times the probability of not picking the class. Okay, so for each possible class contained in there, we calculate the probability of picking the class times the probability of not picking the class, and then again. So in the case of 2, so in the case if we have only 2 classes, then basically our Gini of S would be, so as we had here, so our, so this is the brackets. So it would be probability of picking the first class times the probability of not picking the first class plus the probability of picking the second class. And this we can express since we only have 2 classes. So the probability of picking second class we can write as the probability of not picking the first class times the actual probability of picking the second class. So first class, not first class, second class, not second class. Okay? And if we sum this up, then we can just say basically, so this is our Gini function for 2 classes. And as you see, what does it look like? So we can even draw it. So if we have here probability and here we have our Gini function, then when is this the lowest? So we want our Gini impurity to be low. We want our leaves to be pure. When is it in the lowest? Obviously, when the probability of picking one class is in the highest, or the probability is on other. So if we express it in the probability of only one class, that would mean if we have 0 probability of picking this class, that means we'll pick another class, or if we will have probability of 1 picking the class, right? So here we will have 0. Our Gini impurity will be 0. So we have either leaves of one class or the other class, so our probability of picking the first class would be either 0 or 1, and then you can easily say if we have here 0, then the whole thing is 0. If we have here 1, then the whole thing is 1. So this is what we want. Yes?
Why do we actually bother ourselves with this impurity? What is the problem? The noise in the data?
This is the loss function. This is not loss in the data. This is yesterday, well, our loss was like moving with these distances of some marginalized in hyperplane. And today our loss, we want to somehow construct a tree which classifies everything correctly. So it's not always a good idea to do it like this, but it's what we are moving towards to. So imagine you have some leaf here. So this is actually what you try to do. So imagine you have some leaf here which says 50% of our examples here have one class and 50% have another class. What can we do with this leaf?
But we asked about this class, right? For example, does the person has chi or not?
Yes, but in order to decide what we need to ask, we need to see what the effect of our question would be.
Okay, so we check the attributes and then decide what.
Yes. Yes, so because we don't know which questions we should ask in advance, and even so you noticed our minimal tree didn't have even to check all features, right? So we basically want to find which features give us information and maybe like not even look at other features at all. And for those features, we're looking at thresholds. So in our ideal way, we won't ask so many questions and we won't even look at all the features. And in order to determine which questions to ask, we need to determine what the result would be. And the result, so if we have something here, we need to see which question we should be asking here, and that means we should measure the result of our question. And measuring the result of question means first to be able to calculate this Gini of one node, and then obviously if you split in, you can calculate Gini of others, then you would subtract, and then you have your increase or decrease. So for that, we need to be able to actually say what is the effect of our split, what we will do if we will answer this question. And for this, first, we need to understand how can we actually calculate what's happening in the node? So the Gini, the impurity of our node. And the impurity of our node would be 0 if they have leaves, if we have examples of one class or the other and nothing else. And when our impurity will be highest, it will be highest when we have both classes the same amount, or 3 classes the same amount. So each class, so in the case of 2 classes, if it's 0.5, then our Gini index will be the highest. So this is basically what Gini function looks like. It will be 0 when either 1 or 2, and with the worst, so our worst possible case is we cannot decide everything. We have leaves, examples of both classes equally in our data, and this is the worst possible thing we can get, and we need to reduce it. We need to do something in order to reduce this. Okay, so this is basically what Gini does. So Gini calculates it like this, depending on this probability. And then there is an entropy. It has a slightly different calculation. It asks what is the information content of our event. So now we're not talking about probabilities anymore. Okay, we do, but not in this sense. But we say, okay, what is the information content of event E? And our event E would be the picking the label of our class from the set S. And this formula which you see is just the definition of information content. So this I is for information. And so basically you take the logarithm to the base 2 of the probability of your event. And this logarithm has this notion, so the power of 2. So this is basically either 0 or 1, for example. So it can be understood. It's coming from the information theory where you measure everything in bits. So basically you say how many bits I need to describe my event. So if you know something will definitely happen, I don't know if it will be like cloudy right now and completely like you would definitely know today will rain, then you wouldn't need to bother and to describe it in many bits. You would just say, I don't bother to use the space for it, it will definitely rain. But if something is not supposed to happen, you're not sure, then you will describe it at some point. So the higher probability of some event, the less bits you need to describe it. Basically, that's what it says in this information content function. So if something will be happening for sure, then you need to don't need to have much bits to waste much bits for it, and otherwise you do. This basically comes from compression theory. There you also, if you have something certain, then you don't waste bits on compressing it, and if it's something rare, then you would waste bits for that. And the entropy measures the expected amount of such information. So the first formula would be information content, and the entropy would be going over each class and measure the expected amount of information conveyed by telling us which outcome we will get. So we want to minimize the entropy because we don't want to be surprised. So we want to be certain. So the entropy is high. That means that the probability of this event is low. And we want for a probability that we pick some label of the class to be really high. We want to kind of create order in the universe. We want to be certain. We want, if we go in this set, we definitely pick the label K. That's why we want our leaf to have low information content. So maybe for you to just think about it, we have 2 events, rolling a dice or throwing a coin. Yeah, that's good. So if you roll a dice or if you're throwing a coin, which entropy is highest of which event? Yeah? Yes, because the probability of having one class is lower, correct. So yes, and we don't want that. So we don't want high, we want low, as low as possible. Yes, so this is what the idea of loss function entropy. So we had this loss function Gini, and then we have loss function entropy, and those are both two which are most commonly used. You need to decide it on yourself by trial and error. But once you've decided it, so once you say, okay, I want either to measure my impureness in Gini and entropy, you need to actually calculate what you will be doing by splitting them. So first you know how to describe the entropy, and then you need to basically measure what will I do if I actually split with this question. Yeah, and so for this, once you got the idea, so you maybe don't need to get into the detail, relax, and I'll just explain for those who are interested. So if we, so the idea behind the whole thing is we can now measure the impurity of a set, and what would be good if we measure impurity of the split. That means we have some split, we'll calculate it, and we have some other sets. So here, for example, the set, yeah, if I delete it with this, so this is set right, set left, and this is set right. So this is basically what we have now. So you only need for now to understand that we have this impurity here, we have this impurity here, somehow either entropy or Gini impurity. And if we subtract this, with this, we want this to be maximized. So we want, with our split, to reduce the impurity as much as possible. And this is just for the explanation how we can calculate actually the impurity of this, because we until now only know how to calculate it for one. So we'll briefly go through this. So if we can compute an entropy of a node, what is the reduction in entropy of a split? And this reduction in entropy of the split, this reduction, this minus this, is called information gain, and is given by this formula. And basically what it says, it's nothing simple, nothing hard. It just says, okay, I have this entropy here of this set. I can calculate it. And I have entropy of this set. And now, in order to compute the whole entropy of this split, I need to take this entropy and multiply it by the probability that this actually will happen, that we go here. So how do we compute this probability? We just say, okay, the amount of answers which will go to the left divided by the whole amount. So this is left. And here, the amount of answers which will go to the right divided by the whole amount of answers. So this basically is the probability that we actually end up in this split, and this is the probability that we end up in this split. And we need to basically multiply this entropy of this split times that we actually go in this direction, entropy of this set times that we are going this direction, and then we need to add the whole thing. And this is how we will calculate the entropy of the whole split. And in the end, what we need to minimize is this minus this. Basically, that's that. This is how this decrease in impurity by the split is calculated.
Or do we minimize or maximize the difference?
Maximize. So the entropy should be minimized, but the difference between two should be maximized. Yeah. Okay. And yeah, so this is basically what's behind it. And when do they stop? So now we know basically everything. You saw we have this algorithm of greedy. We decided on our function. We know now how to calculate the effect of the split. We compute in all the possible features with all the possible threshold, take the maximal reduction in entropy, go in again and again and again. And the only thing now we need to decide is when you will be stopping. And this is important because you are in control of this. So there are two things which you cannot control. This is basically if at some point all the labels in your set are the same, then this node becomes a leaf. You cannot do anything about it because it doesn't matter how you split, what you do, you still will get the same label. That means if we at some point reach a node where all the labels are the same, we stop splitting this node and assign it the label we get. So this is the first, which is most common case. The second most common case, if all the inputs are the same. So if we go in there with the same questions and we are here, then that means no matter which leaves we have, we cannot possibly do anything about, because all the questions we have here, all the features we have here are the same. So it doesn't matter what we do. That means in this case, so this is basically can happen when you have noise in your data. And in this case, we will assign the leaf to the class which happens the most. So for example, if you have, I don't know, 10 points and 2 of them are noisy, have other class, then you will assign the leaf that happens the most here. So this is the way how we would deal with this noise. So these are 2 most straightforward stops. And there is this third, which you can control. And this is this. You remember we were talking about this variance and bias, depth, and so on. So in order for us not to split until the end, because that could mean that we have high variance. I mean, that means definitely that we have variance if we keep on splitting until every leaf is pure. Then obviously, if we will at some point introduce variance. And this is the idea which is used in very many machine learning algorithms. It's called early stopping. So early stopping, that means that you are stopping not when you already cannot do anything else, but you say, okay, I see the curve of my loss, training loss. I see the curve of my validation loss, and I see that it already starting overfitting. So if this is a very important thing because it basically happens everywhere. So you monitor your loss, and your train loss looks like this, and you test loss, and not test, validation loss, starting to look like this. Okay? That means we are starting to overfit. And this, if we see it like this, then we say, okay, we are stopping here. We take the tree which we had at this point, because this was our best, so this would be the training, because this is our training set. So we would stop early, not when we did everything, so not when we split it and reduced our entropy like completely, because that would be somewhere here, and for our we starting to overfit. And we just stop at some point when we see convenient based on the validation data. So this validation data is not only important to tune hyperparameter, but also to decide on this stopping early thing, which is also really common in deep learning, for example, and in order to produce refitting. So is that clear? And in this case of decision trees, that would mean stopping earlier after a certain depth, or most commonly after a certain number of splits. So you can say, okay, I've split it enough, I'm already starting to overfitting, so I take the tree as my model, which was here, because otherwise it only gets, so the training results get better, but the validation results get worse. So this is an important thing which you can decide on. And this way you can reduce the variance a little bit in your decision trees. But, so these are only 3 criteria which you can stop. But what we cannot stop is, we cannot stop if no split can improve impurity. So at some point, if you have here, for example, our data set, where we have pluses, 3 pluses here, 3 pluses here, 3 zeros, 3 O's here, and 3 O's here, right? So no matter which split we'll take, here or here, so all others would be even worse, but this split or this split are equally bad, because we basically have still half-half, so our probability will be still, here it was half, the probability of picking the class, and the probability there is also half. So no matter which split this or this will take, we won't improve our impurity. But why is this not a good idea to stop here? Because obviously this set is really nicely separable, right, by splits, just not at this point. And that's why it's not a good idea to stop if no split can improve impurity. That, in this case, we would just select one of the splits and keep on moving. And the reason behind why it's not why it's not a good idea to do it like this is because they are greedy. They cannot look far ahead. They decide only what they see now, and they don't know what happens if we split like this. Because if they do it like this, then wow, suddenly this is really nice. For the next split, we can do it just like this. And then it's separable. We found perfect separation. But before that, we were at a loss. We didn't know what to do. So that's why we don't stop if no split can improve impurity, but we keep on splitting until one of those other three criteria is reached. Okay, now basically we have learned everything about decision tree for classification. There is some couple of notions which you may be already asked into. So the branching factors, we until now focused only on yes or no question, and we will continue using that, because we can also introduce, of course, the questions like, as I said, with this blue, green, and white examples, you can branch more, but it's just not computationally convenient, so it's just usually the binary factor trees are used. Second is, people have tried also to ask more complex questions, not just is equal, the features equal to or less than, but also this kind of questions here. So that would mean that you would partition your space with convex polyhedral regions. They are really complex, and that means, of course, you will probably at some point get better results. Or they tried also to partition it with pieces of spheres. That would be this type of questions. And of course, so like in this way, you're not splitting like by those axis-aligned cuts, but more complicated. And this is a plus. But the minuses are, first, you can cause overfitting a lot faster. And the even most important is it increases computational time by a lot. So that means that this plus is not so important as those minuses. That's why people tried it, and this didn't stuck. So those questions of axis-aligned splits is the ones which are used, in case you are wondering. And here is an example how you can use it for regression. So basically, you don't do anything else for regression. They can be used in completely the same way. The only thing which you need to change is your loss function, because obviously we cannot use our Gini or entropy anymore because we don't have classes, we don't have probabilities right now. And the only difference is, so if our labels is continuous or are continuous, then this is the way to measure our impurity of a set. So basically what we do first is we we say, okay, there are some labels there which are continuous. So I don't know, 1.0, 1.5, 5.6, and so on. So first what we do is we compute this mean. So we first compute the mean of all the labels in there. This mean. And then once we have it, we calculate for each label that for each example that is in the set, how much it varies from this mean. So how far apart it is from the mean in this set. So that means if we have only small variations or no variations at all, then it's good. Our label, our set is pure. And if our variation or variance, you maybe already saw that is really, the formula is basically the formula of variance. So if our variance in a set is high, that means we need to keep on splitting. And this is basically the only difference between classification and regression. And such algorithms are called CART, classification and regression trees, if you ever heard of this. And basically the only difference is the loss function. We now first calculate the mean, and then compare each example, how far away from this mean it is, and if this variance is high, then we need to keep splitting. We are bad, so this split is still bad, and if they are all don't vary much, then it's already fine. And this is basically the graph how it works, step by step. So if we have, for example, some function which we don't know about, but let's pretend this was the function where our examples are drawn from. So we have some examples here. I don't know. So those are our training examples, and we would like to regress this function. Then we will first calculate the mean and so on. So we first will be doing some splits which looks something like this maybe. And then we would basically what we do, so now we're splitting into nodes. We had one node of all points, and we're splitting them into two. And what's happening, we have all those points in one node and all those points in other nodes, and we said we represented everything as a mean. That means we will basically approximate this whole points with the mean, which would be probably, I don't know, somewhere here or what. And this with another mean. So obviously this is a really bad approximation. So if you imagine this is our function and we are approximating it like this, and this is our function and approximating it like this, but it doesn't matter because we can keep on splitting, right? So at first, this approximation of our function is bad, but as we continue splitting, we will then be splitting maybe here somewhere, then our mean will be better, and so on. So we'll be here probably, I don't know, somewhere. Here we have only one example, so here. And if we continue, keep on splitting on and on and on, our means will be near on the actual function. And since we can continue as we want, at some point we will get this function correctly. So they are really strong for the regression also. At least, so with some variations. But as you see, it works. Yeah, so this is basically, that's it for the decision trees. But there's this bias and variance problem, as I already drawn you here. So it's really hard to find this sweet spot having only the depth of splits as a hyperparameter. So basically, we said we need to vary our depth, or we need to vary our number of splits. And it's not really a good way because it's discrete. So what if some underlying distribution is like not allow you to even represent it like this? That doesn't make sense. So it doesn't matter then if you really find this, then it still could be that the distribution is even possible in a better way. So if we only have the depth or the number of splits as a hyperparameter, we cannot do a lot of variations in there. So we cannot really explore the big space. So for example, and you see if you will enlarge this function, this plot afterwards at home, you will see there is basically two Gaussians in there, which are really noisy, but they look like this. So we have here pluses and we have CR0. So those are two Gaussians which are a little bit overlapping. And this is what decision tree does with this. It starts splitting somewhere. So you see all those splits that it made didn't make sense for the class as such, right? So they split it, I don't know, for 1 point only, and so on and so on. So because it's really hard for a decision tree to like vary only one parameter and get results right. So it's because that just means that maybe and even often possible that even if we explore the whole possibility of the depths and number of splits, the actual result will not be there because it will be something in between, and we cannot reach it because we only go in with discrete steps. But yeah, and so this is basically a bias variance problem. So if we are too low on depth, and then we go have high bias, and we have too far, we have variance, but we cannot really control both more than just vary this. And this is basically a problem of decision trees. yeah, because the number of splits, it might be even not possible to find this sweet spot. So this sweet spot is called this where we are not overfitting much. Yes, and so this is the reason why the decision tree usually don't work very well without anything else. So they are really bad without any modification, but the good thing about them is that they are easy to understand, and they have this clear definition of this bias and variance problem, and there are two effective ways to deal with these problems. And once we deal with them, we will be strong. So one way to deal with them, with these problems, is make the tree small. So we make it small, and then we have a bias problem. And we accept that we have a bias problem, and then we will address it with a method which is called boosting. So there's some algorithm which are called AdaBoost or gradient boosting, which are really, really powerful. But we will not go into this detail because the idea behind that is really similar to decision trees and bagging. So that's why you will, after you understand today what we're doing, you will be definitely able to work with boosting also. But it's a little bit harder to understand what's behind it. So you can just remember that boosting makes the decision trees really small, and then uses a lot of those small bad classifiers, estimators, to make one good estimator. And what we'll be doing today is we will be making the tree very, very large, and we will accept that we will have variance problem. So very large means we will split until we cannot split anymore. We will make all our leaves pure, and then address this variance problem with bagging. So this boosting and bagging are basically both things which are not only applicable to decision trees, they are applicable to, so boosting is applicable to all algorithms which has bias problem, bagging is applicable to all algorithms which has variance problem, but especially with this decision tree, they like really get a strong estimators and how it works. So it's basically only small adjustments. So actually we're already done with all of this theory. It's just how can we do to address this variance problem? What can we do? And in order to understand what's behind this, we need to understand why actually large decision tree have variance problem. And if you think about it, so we splitting, and they don't have a variance problem at the beginning, right? So in the beginning, they splitting, they have good decisions. Only in those lower levels, we get the variance problem. So low-level splits are very data specific. So at the first, we have a lot of examples in there, and we can draw from a lot of data, and these probably are good splits. But in the end, as with this Alfred and Ty, so we actually basically split it only for one example. So those lower splits are very data specific. And that means if we would reshuffle the data somehow and get another data set, then we will get totally different classifiers if we will do it, if we split until the end. So those levels would be similar, but those lower levels will be totally different, and that means in the end, our classifier will be totally different, even though we had basically only small amount of data which actually determined this classifier, because they were low-level splits when we already have nodes with only a small number of examples. We still keep on splitting. So this is where this problems occurs. So so because the splits will be made in totally different dimensions, we will be asking for other features, other so on. So so this is the problem: lower level splits. And so if the variance is large, that means the difference from the expected classifier is large. And what we need to do to reduce the variance? And the idea is actually very simple. We will just take a lot of data sets. So not just one, but a lot. Since our problem is this variance on other data sets, since we had that each data set will lead to a totally different classifier, then we will say, okay, no problem, we just take m data sets. And then we will train own them, and then we will have a lot of different classifiers, and then we will average them out. So we will take m data sets, train a decision tree on each data set, and then we will have, I don't know, m classifiers, and for each new example, we will apply all our classifiers on this. They will all get some results, and then we will get the average label, average score, and we will classify it like this. So for classification, we will obviously take the one which occurs most, and for regression, we will take an average value. So this is a good idea to do this, of course. So if we had this m data sets, then this idea is really great, actually, because that means that you will, up until some point, get really good splits, then you will get bad splits. But if you have several of such bad classifiers, then everything will be averaged out, and you will be fine, because there is this weak law of large numbers, and the following holds. If our number of data sets goes to infinity, then our classifier, so this whole classifier which averages the predictions, will go to the expected classifier, will be really, really near. So this is the law which actually exists, and it holds, and it's fine. But where's the catch? So where do the m data sets come from? And the problem is, should we define, we only have one, right? And should we define it as into m disjoint parts? Is it a good idea to do this? So imagine we have a data set of, I don't know, 1,000 examples. Should we divide it in 10, 10, 10, 10, or 20, 20, and so on? Wouldn't this be a good idea? No, it wouldn't, because then we wouldn't gain much. We still have those same amount of examples seen once in the same, basically, yeah. So if you do it like this, you won't gain almost anything, so this won't work like this. So how can we help? And the better idea is bootstrapping. So the bootstrapping is basically came from, I don't know if you know, there is this Baron Münchhausen who was lying the whole time, so there are tales of him, and who was lying on it all the time. And one of these stories was that he was going through snow, which was really deep, and afterwards he was asked, how could you possibly go through the snow, because it was so deep you could sink in it, and he said, I just put myself by my bootstraps. Okay, so actually it's a lie, but the idea stuck, and this is what we will be doing. We basically be doing something which, yeah, lying ourselves into doing something which we already have, and thinking about it as if it would help us to achieve something which we cannot actually achieve. So, it will help, like, a lot. You will see. So this is why it's called bootstrapping. And bootstrapping means we can create our m different data sets by sampling endpoints with replacement. So if we had, for example, our data set would be, if it would be like, I don't know, containing of, just take a simple example, A, B, C, D examples, then we will create, so this would be our original data distribution, and we will create m different data sets by sampling endpoints, so the number should be the same, but with a replacement. So our data set could look like this, our new one. So our new could be one, I don't know, B. The second one could be, I don't know, C, D, and whatever. So this is how the new data sets look like. So that's why this idea bootstrapping, so we basically pulling ourselves by the bootstraps, right? So we create a new data set out of our original one by sampling with replacement. But as you see, they are not totally the same. So of course, we have only our original examples, so you will all find them here. But the weights of those examples is not the same. And this is a really good thing, because that way, roughly 60% of data in each data set will be the same, roughly, right, on average, but roughly 40% will be different. And of course, this doesn't solve the whole problem, but it will help to reduce our variance. And what we wanted to do, we just said our variance is too high, we want to reduce it as much as possible, as much as we can, and this idea would already help by a lot. But the problem is why this weak law of large numbers is violated in this case, because we said if we take a large amount of data sets, our average classifier will go through actual average classifier. And of course, we didn't say, but there is a sub-node of this weak law of large numbers is that the data set should be independent in order to be able, but in our case, they are obviously not independent. So independent here means in the statistical, stochastical sense, that means if you seen one data sets, you're not able to predict what happens next, and here, of course, you can predict because they are drawn from the same distribution. So they are not independent. But it's not a problem because it's enough to make the variance term decrease, and this is what we want. So we want first to make the variance term really, really large, and then we want to decrease it. So this was the idea of bagging. If you have estimators where you have variance problem, then you can create out of your data set a lot of other data sets which are drawn from the same distributions and train an ensemble of estimators. So this is called also you will stumble in the Paul ensemble learning. So this bagging and boosting are all ensemble learners, where you have a lot of learners which are created on different data sets which were drawn from the same data set, and then average the result out. And it works really, really well on estimators which have variance problem. And random forest is based on that. It has basically the same idea to create such data sets from the original data set, but it has one nice twist. So we will do basically the same as bagging, but for each so first, for each of new data sets, we'll train decision tree until only pure leaves remain. So for all of those M data sets we will have huge variance problem. So all decision tree we create will have huge variance problem, but we have M of those. And then, instead of trying all the splits, so when you are splitting for each split, instead of trying all possible features and all possible thresholds, random forests do another trick. Not only bagging, but this, they say for each split, we randomly decide on which features we're going to ask. So this is another variation. So this was already a variation, but for random forests, they vary even more. And they say we're not deciding on all our possible features, but for each decision, we will randomly draw k features and compute the information gain only on those. So we ignore for those others and split based on that. So as you can imagine, your decision trees will be even more far apart from each other if you do it like this. So here they are always already far apart, so all other decision trees. But if you do it like this, if for each split you not choose going through whole feature set, but only choose k, smaller number, then there will be even more variations. And yeah, that way we get very different decision trees which make different mistakes. So remember, we said our low splits make mistakes. But the good thing about decision trees, they do something right, because otherwise they wouldn't work at all. So there are a lot of things which they do right. So that means when we're splitting, our our mistakes will be averaged out. Because with each decision tree, we will do something right and something wrong. And all those rights will remain. And all those mistakes, or many of the mistakes, will be averaged out when you compute your average label or your most frequent label out of the things. And this is the general idea behind the random forest, and this works really, really, really well, as you will see today, in comparison to decision tree. And basically, only thing which is remained is how to set k and m. Those are hyperparameters. But good thing is there were this research made, and it was found out that if you set k to this value, where d is a number of features, so set k to the square root of the number of features, rounded up, and set m as big as you can afford. So if you can afford to wait long, set m as long as you get. So basically, you don't have any hyperparameter here, and this is really good for us, because we know how hyperparameter can change your results. So the only hyperparameter basically with decision tree is this: if you classify chosen between Gini impurity and entropy, but those are basically not actual hyperparameters, because you already know how to set them. I think it's preset even in things like this. And here you can just choose, like 100 or something, and or 200 or whatever, and you are done. Yes?
And for this decision tree, how do you take the final decision? What is the object?
Yeah, we just
Averaging.
Yeah, for one decision tree, we basically don't average anything, but we traversed. So we start with an example, and we start asking the questions which we have here. So first we ask this, then we go here and go here and go here, and then at some point we will land in some leaf, and then we will assign our new test example this leaf that we got.
Yeah, and for different trees?
Yes, and for different trees. If you have classification, you will have 10 different results, and you will take the most frequent one. So if you have 5 results for class 1, 3 results for class 2, and 2 results for class 3, then you will take the first class. And for the regression, you will take the mean, the average. So you will get some results from your algorithms, and for the mean, you will calculate for your final result on your test example. You will calculate the mean of all those. Yes. So yes, and in this case, really, the result will be much different between decision trees and random forest, and the same also goes for boosting. The algorithm there is a lot different, but the idea is the same. Take decision trees as weak learners and enhance them by some future operations. So basically, almost all characteristic which apply to random forest go also for boosting. So the pros and cons of decision trees. So they are very fast to train and evaluate, relatively easy to interpret, but big minuses, it is not as good as other state-of-the-art approaches. But the plus, again, is that they have this clearly defined bias and variance problem, and we can address the problem of high bias with boosting or the problem of high variance with bagging. And that way, they can be used as weak learners with boosting and bagging to define effective algorithms. And pros and cons of random forest: they can first deal with imbalanced data. You don't really need to care that your data should be balanced. Second, they don't really have hyperparameters that needs to be tuned. Third, they can deal with missing values without a problem, and also with unpreprocessed data. So you remember yesterday and on Friday, we had this classifier or learners which rely on distance metric. And for distances, we almost always need to preprocess the data. And here, we don't care about this. We can just drop our data on the decision tree, no matter if it's categorical. So you can have some features can be categorical, some features can be numerical. We don't care. Just throw anything in there, and it will work, which is really good. And some people say it's at least a second best algorithm for many problems. So there is a custom tailed algorithm which will work better, but the random forest is almost always at least a second best algorithm for many problems. Yes, and as a side note, as I already said, this idea of bagging can be used with many machine learning algorithms that has variance problems. So if you at some point notice this, and also early stopping. So those are two ideas which you need also to take from this lecture. So first, if you notice something like this, then it is a probably good idea to stop early. This is basically a sense of regularization. So this also belongs to regularization, early stopping. And the second is this bagging. If you admit that you have variance problem, and then you train an ensemble of learners and average them out. So for you to hope that they will do, so what they will have in common are the correct things, and what they will have different are mistakes. And so the hope is that the mistakes will get averaged out. Yeah, that's it.